Okay, so we'll go ahead and get started. We're going to continue this discussion of alkene addition reactions. And again, we're looking at this point, adding heteroatoms to the two sp2 hybridized carbons of the alkene. So these specific reactions that we're looking at for finishing up alkenes basically involve oxygen. And then we're going to transition into the chemistry of alkynes, which will start today and then finish Friday. So this first reaction is called dihydroxylation of alkenes. So here's a general alkene with unspecified substituents. We're focusing in on the carbon-carbon pi bond, which is the nucleophile. In this case, the electrophilic reagent is called osmium tetraoxide. Then we have this species here, which is a benzene ring with a nitrogen in it. So that's called pyridine, which is a base. And then what this smaller I and double I, so 1 and 2, these basically means all of these conditions are run in the same reaction, but just sequentially. So you have your alkene, then you add these, then the mechanism proceeds to add the oxygens to each carbon. And then after a certain amount of time, you add this reagent, sodium bisulfite, which is a reducing agent that gets rid of the osmium basically. And so what ends up happening is you end up with a 1,2 diol. These are commonly known as glycols. So for example, if you did any driving today, your car has ethylene glycol and water as the coolant for the engine. So ethylene glycol is basically has physical properties that allow for cooling of the automobile engine. They give it sort of like a green color so that if you know if it's leaking, that's what it is. And if you've ever had an animal lick this up off your driveway, it's extremely toxic to the liver. And so animals that like the taste of this because it's sweet, they will end up dying because it essentially shuts down liver function. So these are called glycols. And so let's consider this substrate here. This is an alkene. We're treating it under dihydroxylation conditions, and I've left some space open for the products that are formed. So let me give you some hints about the mechanism. I'm not showing you the exact mechanism of this because it gets pretty complicated. Essentially, this is an oxygen-rich compound, osmium tetraoxide. 2 of those oxygens are transferred to the alkene, and so it does that in a syn fashion. So syn basically means addition to one face at the same time. So syn, and then concerted, we'll use that word as well. Concerted has to do with the timing. So concerted, we mean both oxygens are adding at the same time, and syn means they're adding from the same face. So if you consider that, let me ask you a question in the chat here. How many faces of this alkene starting material do you see? So how many faces, hopefully we understand what I'm trying to convey here. How many faces of the alkene pi bond are there? Face. What I'm pointing at right now, my face. So Aiden says there's 2 faces. So now consider the way that we are viewing this whiteboard in that if the osmium tetroxide is coming down from the top face, that's one mode of syn addition. If it's coming up from the bottom face or behind the screen, that's another mode. So how many products are formed if we're forming a 1,2 diol from that substrate? And what is the relationship of those products to one another? Giving you sort of a clue here. The starting material is achiral. There's no stereogenic centers, and all of the reagents are achiral. So again, as we transition into 256, those are words we'll use a lot. So starting materials, reagents, and then products. So if you're really into chemistry, a chemical equation sort of resembles an English sentence. You have some nouns, you have some verbs that act upon the nouns and they produce something. So you have, the subject, the verbs, the predicate. So you have the subject, the verbs, these do the acting, and then the predicate. So that's sort of a format. So if you've drawn out the products, how many products do you see, and what is their relationship? So maybe I'll start off, and I'll put this into some perspective here, just because I like to draw. So now I'm going to use my handy dandy eraser. Just going to erase the pi bond. I just set it up that way so you can see the face. So if we add from the top face, again, I said it's a syn addition. So that's what I mean by syn. Both of these OH groups added to the same face. So Aiden says there's 2 enantiomers. So that is correct. So I'm gonna draw using the same orientation as I did initially. I'm going to go ahead and erase the pi bond. Then I'm going to show the OH groups adding from the bottom face. And to show you what Aiden has proposed, these are enantiomers. This is not a stereogenic center because essentially there's symmetry within that ring. So these are the same, these are the same. So this is not, but this is. So if you can imagine taking this structure and sort of doing a rotation, so you form the mirror image, you will see that this stereogenic center mimics that one. So you have one stereogenic center. These are the enantiomers. Now, just as a review, if this is achiral, all of these are achiral. What is the ratio in which these are formed? So the question is, what is the ratio of the 2 enantiomers? Do you favor one over the other? Or do you favor one completely? So Blakely says they're formed in 1-to-1 ratio. That's correct. And so I just want to take a minute to explain to you the consequences of that. So this is achiral. All of this is achiral. You are producing two molecules. These enantiomers have stereogenic centers. That is a fact. But overall, because you are producing them in a 1-to-1 ratio, overall the material itself is achiral. That's what we mean by this 1-to-1 ratio, even though you're forming both of these enantiomers. And so I would say maybe in the late 70s, chemists really started to think about this issue. This is achiral, and we're producing this achiral material that's in a 1-to-1 ratio, but how do we get around that? What if we do not want achiral? What if we only want to produce one enantiomer of something? And so there's been a lot of work in biochemistry and the understanding of enzymes, which are chiral. And so chemists started to think in those terms and basically introduced extra sort of reagents into this brew. And I'm just going to, in general, call them ligands. So osmium is a metal, right? It's a transition metal. A ligand is basically an architecture that you can put around the metal. So specifically, chemists looked at developing chiral ligands. And so the ligand itself creates or induces asymmetry so that you can selectively add or block one face of the alkene. So these ligands, if you've taken any sort of linear algebra or advanced math, you've talked a lot about actually symmetry elements. So in chemistry, we call that C2 symmetry is the most common one used for a chiral ligand. And I just like to think of a C2 ligand as something that has a 180-degree axis of rotation. And to just explain that simply, it's sort of like if you just rotate it 180 degrees, you get the same thing. That's sort of the most common C2 symmetric ligand. I can draw an example maybe to clarify what I mean by that. So this transdiamine would be C2 symmetric. And so the axis of symmetry would be, imagine if you were rotating that axis, this wedge would become a dash and that dash would become a wedge. So by having that pre-existing chirality sort of in something like this, you could favor one or the other. And that's really where organic chemistry is at nowadays. So before we move on, I'm going to show you alternative conditions to this that uses the following reagents. So I'm just going to be general with the alkene. So there's our alkene. Alternatively, we can use this compound potassium permanganate in the presence of sodium hydroxide and water. So that's sort of the first initial step. We run this sort of at a cold temperature. and then we do an acidic, a dilute acidic workup, and that affects the overall dihydroxylation of the alkene as well. Any questions before we move on to the next oxidation reaction? So now we're going to look at another reaction that's adding oxygen to the sp2 hybridized carbons, but we're still using this reagent, but the conditions are slightly different. And so this is an example where knowing the details matter, because what changes now is this symbol here, this delta, which means heat. We're using the same conditions that did the dihydroxylation, but the presence of the heat actually goes further, and we transform our alkene. So I've labeled C1, C2. We actually add oxygens to each. We then cleave the sigma bond, and what we end up with is now two species, both of which are carbonyls. And so this reaction, you have to pay attention to what these substituents are bonded to C1 and C2 to understand what functional groups you end up with. Because if you think about all the carbonyl functional groups you've learned, the possibilities are ketone, carboxylic acid, or carbon dioxide. So examining what those substituents are, you can then predict what type of products are produced. So let's look at some examples so we can see what's going on here. So KMNO4, heat, sodium hydroxide, water, and then we're going to do a dilute acid workup. That's what we mean by hydronium. Now what I'm going to do is identify carbon, maybe I'm just going to put dots, if that's okay. I'm going to say this, the red dot and the blue dot identify the two sp2 hybridized carbons of the alkene. So what I'm further going to do is I'm going to draw a dashed line through that pi bond. So there's where the oxidative cleavage takes place. Now this is where you have to pay attention about correctly predicting the products, because each carbon is becoming a carbonyl. So if we're cleaving here, this carbon is then becoming a carbonyl. You have carbon-carbon. What is the functional group from this portion? We're cleaving. We end up with the western and eastern fragments. The western fragment should be what functional group? If you have carbon-carbon. So Max says ketone, so let's draw that out. So now over here, if you look hydrogen, carbon, we would say, okay, this should end up being an aldehyde. But notice I did not write aldehyde over here. So the issue is when you have an H, that gets further oxidized from an aldehyde to a carboxylic acid. So that fragment, eastern fragment, actually ends up being this. Which is a carboxylic acid. So again, I'm not going to show you the mechanism of how that happens. It gets pretty involved, but what I sort of want you to just follow the logic. That when you're identifying the two sp2 hybridized carbons, you look at the substituents. If they're both carbon, you always end up with a ketone. If one of them is hydrogen, you do not end up with the aldehyde because that gets further oxidized to the acid. And if you're taking 256 with me next semester, the framework in which I teach 256 is based on functional group oxidation state. So we progress from oxidation states 1 to 2 to 3. And what do I mean by that? If we look at this ketone, the carbon with the red dot is the only carbon of that ring that has heteroatoms bonded to it. And when we're considering oxidation state, you're simply counting the number of bonds to that heteroatom. So we have 1, 2. We do the same thing for the blue carbon, 1, 2, 3. And when we start learning about further functional group transformations of ketones and carboxylic acids, we overlay a nice logical framework using the concept of oxidation and reduction. Because if I tell you the ketone can be reduced to an oxidation state of 1, and this is a good question if you're following the logic, if this gets reduced to an oxidation state of 1, what is the functional group that is formed? If you know it, you can put it in the chat. So Mac is pretty quick. He says alcohol. So yeah, that's the logic we're using. And as you'll see, oxidation reduction reactions go back and forth. So redox. You can go from 2 to 1, that's a reduction, or 1 to 2 is an oxidation. So that's a preview of what we're going to do next semester. So now let's consider another example, just so we're all following. I'm going to write ditto marks. That means the same conditions as above. And so now what I want you to consider in this molecule, the overall question is, how many products are formed? That's one question to consider. And how do you get to that question, or how do you get to that answer? How many pi bonds are in the starting material? And therefore, how many sp2 hybridized carbons are in the starting material total? So Blakely says, so we have 4 sp2 hybridized carbons. So I'm feeling pretty colorful today. Let me do the following to help ask some questions and help get some answers from you. This one's red. This one's blue. This one's green. This one's yellow. So over here, so what do I mean by this? So we've identified 1, 2, 3, 4, and we're using the color to help communicate. So the red, what functional group does the red carbon end up with? The blue, the green, the yellow. Let's just first identify the functional groups, then we'll actually predict what the products are. So the red ends up as what? And you're considering what is bonded to that red carbon. So this is what functional group? The blue ends up as what? So Max pretty quick, CO2. Very good. So how was that spotted? You have H and H. Because each of these are hydrogen, you end up with an aldehyde called formaldehyde. That gets subsequently oxidized to carbon dioxide. So CO2 is really the special case where the carbon of the pi bond has two hydrogen substituents. So now the green carbon, what does it end up as? So I've wrote those in to just help. You have hydrogen, carbon. This would end up as an aldehyde, but aldehydes get further oxidized to carboxylic acids. And then the yellow carbon ends up being what? Sort of the same scenario, carboxylic acid as well. And so by thinking of this logic, we're guiding ourselves to the correct answer, and we cannot be wrong. So looking at this, and then I'm going to do something else to help you out as I did before. I'm saying that this gets cleaved and that gets cleaved. So the next question is, how many products are you producing? This may seem like a trick question, but it's really not if you're following the carbon backbone, which is sort of the intent of what I'm asking. If you follow the carbon backbone and see all the connectivity, does anyone say 1? Can we rule out 1? So let's just go through it and you'll see how you logically get to the right answer. So we're going along. Here's our red carbon. We said that ends up as a ketone. So there it is. We've now cleaved that bond. We said the blue carbon ends up as CO2. There's that carbon. Now we're still following this backbone. We go out here. We said that was an acid, CO2H. That's the green carbon. This bond here is still connected. Then we're finally getting to the other sp2 hybridized carbon. That becomes an acid as well. So we're ending up with, it looks like, 2 possible products. So again, the reason for that logic is because this alkene is tethered together through the ring. So it's not splitting off to form 2 different things. So that's why you don't end up with 4 or 3, is due to the fact that it's a cyclic system. So again, that brings up a good point. When we talk about reagents, in the word I want to use is called chemoselectivity. Chemoselectivity basically means that these reagents will only act upon certain functional groups. And what that sort of means in the simplest sense is this ring structure that backbone does not get cleaved through any action of those reagents. So we're being very rational about how we approach these, and we're not adding things in or taking things out that we can't just make stuff up, basically. So this is called oxidative cleavage with potassium permanganate, and we're doing it under conditions that will oxidize the carbonyls further. What I want to do on the next slide is talk about another set of conditions called oxidative cleavage using this reagent, which is ozone gas. So these conditions differ from the prior ones in that when you're examining carbons 1 and 2, whatever these other substituents are, they translate directly into being either a ketone or an aldehyde. There's no further oxidation of the aldehyde to the acid. So this is called a reductive workup. So here's our general alkene, carbons 1 and 2. Ozone gas, when dissolved in dichloromethane, forms a nice bluish hue. The gas acts upon the alkene, and you run these reactions at -78. If you've done lab research or you're going to join a lab, -78 is pretty common. This is dry ice, which is solid CO2. Mixed with the ketone propanone. So that forms that bath. You bubble the ozone gas through to get a bluish hue. Then you either work up with dimethyl sulfide or triphenylphosphine, PH3P. So pH is phenyl. There's 3 of them on phosphorus, so that's triphenylphosphine. And these are reductive conditions. So let's go ahead and look at an example of this. So anyone ever live up north is a question. So I'm from Wisconsin, and when it would get really cold out in the winter, there was almost like a smell to the coldness. I know that sounds weird associating like smell with temperature, but ozone gas sort of has that smell. It smells sterile, very pungent in a way. It smells like winter to me, if that makes sense. So here we have our pedagogy in terms of the colors. So each sp2 hybridized carbon is identified by a color. I've said there's a reductive workup. So when you're identifying the substituents bonded to each carbon, all you're doing is adding a pi bond to oxygen. So the red carbon should end up as what functional group? So the red is the aldehyde, and then the blue is what? Blue is ketone. And so everything you've learned over this semester, we're now taking those words and transforming them into a structure. That stays intact. Here we go. Here's the red carbon. We're now adding our pi bond to it. We've done the oxidative cleavage. Here's the blue carbon. We now add our carbonyl pi bond to it. So we end up with an aldehyde and a ketone. So ozonolysis is a pretty classical reaction in organic chemistry. Again, I haven't gone through the mechanism of how this happens. It's pretty steppy. It is interesting. It's most likely in your book for you to review. But conceptually, I just want you to be able to understand the logic. When you're looking at a substrate with an alkene and you see these conditions, be able to predict what each ends up with and then convert it into the appropriate Lewis structure. So if you're following the prior slide, I used the term oxidation state. So what is the oxidation state of each of these functional groups? The red is at what oxidation state? So 2, and then the blue is at what oxidation state? 2 as well. So really, if you appreciate and understand that logic, the reason why I teach it that way, and whether you believe me or not, the reason why I teach it that way is because in 256, you are going to learn a lot of reaction conditions. And a way to relieve the mental burden of the whole slew of conditions that you're going to learn is if you understand oxidation state, then you can look at the reagents. In knowing your chemical intuition, you can say, I think this reagent might do an oxidation or it might do a reduction. So, for example, the ketone could be reduced to a secondary alcohol. And so by using that logic, you can rationally predict things, because we do not want to use the mentality of like, I have no idea, I don't know, where do I start? We want to be very rational about proceeding through solving these problems. Any questions before we move on here into alkynes? So on this slide, I've sort of pre-drawn quite a bit of material that I'll walk us through to help us understand our journey from the start of the semester to where we're at now, and really where things, again, are going for 256, because 256 is all about the chemistry of the different functional groups. And again, the way that I teach it is according to the progression of oxidation states. So we've started off with alkanes. By now you should know, associate the word alkane with this molecular formula, CnH2n plus 2. There's no degrees of unsaturation. And so this is what a general alkane looks like. The CH acidity is the weakest acid there is, topping off at about 50. The central sp3 hybridized carbon-carbon bond has this distance, 1.54 angstroms. That bond dissociation energy is 347 kilojoules per mole. Now conceptually, if we remove two hydrogens, so a molecule of hydrogen gas, watch this 2n plus 2, we're removing 2. So minus 2, we end up with an alkene, that's CnH2n. Removing that installs the degree of unsaturation, which is the pi bond. The CH acidity, it decreases a little bit, so it's 45, but it's still a pretty weak acid. Notice the bond length shrinks from 1.54 to 1.33 angstroms, and the reason that is because you have increased electron density between the two carbons now, so they're more attracted to one another. The bond length decreases. If we use the respective 347 for the sigma bond, the pi bond adds 264 kilojoules per mole. So overall, the double bond is 611 kilojoules per mole of energy. So this bond total is stronger than that bond. Now look here, CnH2n, we take away two hydrogens, we end up with alkynes. CnH2n minus 2. We go from 1 to 2 degrees of unsaturation. We now have a triple bond, and the acidity has increased quite a bit. This is not a difference of 20, but 10 to the 20, because remember, the pKa scale is a logarithmic scale, so 10 to the 20 times more acidic. The bond distance shrinks again. There's more electron density. We've added the second pi bond. It's a little bit weaker than the first one, but overall we have 837 kilojoules per mole of energy. So that's sort of the progression of our hydrocarbon functional groups. And again, these are the foundations of which modern civilization really is built upon, in that these things come from petroleum feedstocks. So, companies like Shell, British Petroleum, BP, Lucas Oil, all these large oil companies, they get a lot of bad rep for some environmental stuff that they do, but the way we live is based upon the science that they have progressed, because they take this crude oil and they basically, it is transformed into everything we know. If you go on to take biochemistry, there's plant-based oils, and those are important as well. We consume them for food. We can also make certain products out of them as well, consumer products. But really the hydrocarbons are important because they serve as a foundation for everything we'll learn in 256. So there are two types of alkynes. There's terminal, and what do we mean by terminal? The terminal alkyne has the CH. The internal does not. So R and R prime just specify different carbon groups. Again, terminal has this CH. We'll see in a slide or two that basically you make the terminal, or you make the internal alkynes from the terminal ones. We said this proton is acidic. We deprotonate it. We generate a carbanion, negatively charged carbon. We then do an SN2 reaction with some electrophile. So carbanion plus electrophile gets the internal alkyne. So some brief nomenclature. So there's ethyne, propyne, so now we have 1-butyne, or 2-butyne. So we have C5, we can have 1-pentyne or 2-pentyne. So there are the sort of Lewis structures of those rather than drawing out explicitly all the carbons and hydrogens. So it's important to just remember that when you see a terminal alkyne, this there's actually an H there, carbon, carbon. This is an H, so just remember that. So this next slide, I'm just going to take a brief sort of moment to talk about the hydrocarbon gases and what I was referring to about why they're important in society. So if you think about, like caveman and fire good, if you think about like you yourself, the life skills you have, if you were taken to a deserted island somewhere and you had like nothing but the clothes, no cell phone, just your clothes, could you start a fire with the knowledge and skills that you have? So you need the fire to stay warm at night. So just think about that. So Ian can. So what's available to use? Whatever's on the island. I'm going to say some sticks, some shrubs, some stones. So that fire that you're creating keeps you warm. Now I want you to think about the evolution of human civilization, from that sort of fire to the fire that is needed to cut through metal. So it has to be much hotter, right? You need significant amount of heat to, say, cut through steel. And so this example is really meant to show you how alkane, alkene, and alkynes differ in the heat that they produce using the combustion reaction. So we're looking at the C2 series for each sigma, pi, 2 pi bonds. As Ian says, here's the oxygen, here's the fuel, and then the spark source. Those are the three things you need. So now look at how these are all the same. You have oxygen, CO2 is produced, as well as water. So I'm going to go ahead and right now balance these. Again, this is not anything you have to memorize. It's just to show you why this stuff is important for life. So those are the stoichiometric coefficients for the oxygen in each. Now the CO2, 2, 2, 2, so that stays the same. Now the amount of water changes to 3, to 2, to 1. Now what I'm going to do is sum. I'm going to sum these coefficients. 2 plus 3 is 5. 2 plus 2 is 4. 2 plus 1 is 3. So these numbers are important because we're going to use them right there where my arrow is, where I've drawn this arrow. This number is going to be used there. Now the heat produced through this combustion reaction is the following, and these numbers are in kilojoules per mole. This reaction produces negative 1,561 kilojoules per mole. So Blakely, you can just rewatch the video anytime you need. This is going to be posted on YouTube and Canvas. What you really need to just pay attention to is the logic that's being talked about. So this reaction produces this much heat. This reaction produces negative 1,410. And then finally, this reaction, negative 1326. Just looking at that information, just the information in this column, which one do you think is the best to use when you're trying to cut through a very hard substance like a metal? Again, the larger this number, the more heat that is produced. So yeah, your logic would say this would probably be the best. But now what we have to do is take these numbers and normalize them using the quantity of moles of gas produced. So we take this number divided by that. This comes to negative 312. This is negative 352. And then this is negative 442. So in all actuality, even though this produces the least amount of heat, when you normalize it on this scale, this is the best gas to use. So this compound, we said it was called Ethyne. It's also known as acetylene. So has anyone ever heard the term acetylene? In what context have you heard it in? So oxy acetylene, typically what you have is a cylinder of oxygen, a cylinder of acetylene, and that's an oxy acetylene torch. So you turn both gases on, you run it sort of into the same sort of handheld torch, you spark it up, that creates your fire, and then that is strong enough, produces enough heat that you can actually cut through steel. And so oxyacetylene torches are pretty common to do like metal fabrication and cut through things. So welding is slightly different because you're fusing the two metals together, whereas an oxyacetylene you're actually cutting them. But really, I think just so that you have a sense of wonderment, you know, I firmly believe you should take a meaningful message from each class you take. The fact that we as human beings have figured this stuff out on our planet Earth has advanced us to where we are in our current state of civilization. So if you take away anything from this course, just be it a sense of wonderment of things in everyday life, in how we live our lives. So I think I'm going to stop there for today, and then on Friday we'll continue on with the synthesis of alkynes and then the subsequent addition reactions to them. So your